In this video we'll have a look at how to determine the arc length on a circle. There are two examples that follow towards the end of the video, and both of them use angles given in radian measure. So how do we determine the arc length? Well, if we know the circumference of a circle, it's a matter of working out what fraction of the circle that arc occupies. And we know that the fraction is based on the angle which subtends the arc or faces the arc. That angle, which we show here as theta, is a fraction of 360 because 360 degrees is in the whole circle. So we can work out the arc length by looking at that fraction of the circumference, or theta on 360 multiplied by 2 pi r. Now that works well if the angle given is in degrees, but what about if it's in radians? Well, the equivalent amount of radians of 360 degrees is 2 pi, so we can change our formula to be theta on 2 pi multiplied by 2 pi r. Now the 2 pi's conveniently cancel when we do the multiplication, so we're left with the arc length being theta r, or we'll express it as r theta. It is very important to note that this only works when the angle theta is given in radians. Let's have a look at an example now. Now in this situation we're being asked to work out how far a minute hand travels. Now we know that a minute hand travels on a clock in circular motion, and we can see that here with the pink arrow. So it represents an arc length. We've got the information given to us in terms of the radius being 6 centimeters and the angle theta that subtends the arc being 4 radians. So it's a very simple multiplication, and 6 multiplied by 4 gives us 24 centimeters. For example 2, it might be wise to pause the video here, read through the example, and see if you can create your own diagram prior to us looking at the solution. So let's start by drawing our circle of radius 2 centimeters. What we'll also do then is add our minor arc, which is shown here in red. Now it's called a minor arc because it occupies less than half of the circle. Also the angle which subtends that arc is less than pi radians, or less than 180 degrees. We'll place the chord with the orange line, and it has its endpoints at the end of the arc. Now to solve this problem, what we'll do is we'll create a triangle in the circle such that the angle at the center of the circle also subtends the chord as well as the arc. Now we need to establish the angle at the center of the circle. We can do that because we know the formula for the length of the arc, which is L equals r theta. We've got a radius in this case of 2 centimeters. We don't know the angle, but we do know that the arc length is 2 pi on 3. Now we can solve that by dividing both sides by 2, and we end up with the angle being pi on 3. Now to help us solve the length of the chord, what we can do is split the triangle into 2 equal parts. A line that goes from the midpoint of a chord to the center of a circle creates a right angle. And we can see here we've got 2 equal parts of the chord, and we've got our right angle. We're now going to focus on the smaller right angled triangle that we've created. We'll label x for a half of the chord, and the angle at the center is pi on 3 divided by 2. Another way of saying that is to multiply pi on 3 by a half. In other words, work out what a half of pi on 3 is, and that comes to pi on 6. So in our right angled triangle we can determine x using trigonometry. We know that the sine of an angle is equal to the opposite side divided by the hypotenuse, and in this case the side opposite the angle is x and the hypotenuse is 2. So we can write that as the sine of pi on 6 is equal to x over 2. Now the sine of pi on 6 can be found using exact values. That's a half. So a half equals x on 2. And we can easily solve that by saying x must match it and equal 1. Therefore the chord length is double that, and that's equal to 2 centimeters.